Hello everyone! Now, in this last video, we covered extrema and maximum and minimum points. We also covered intervals of where the function increases or decreases. So all in all, we covered basically the first derivative, the use of the first derivative. Okay, and finding the maximum and minimum points, relative and the absolute maximum and minimum on an interval. In this video, we're going to be analyzing the second derivative. Okay, and see how the second derivative is useful to us when analyzing functions. And what the second derivative is useful for is how the graph curves. How the graph curves. Okay? Now, you have to first realize what f prime prime of x actually means. F prime prime of x is actually the derivative of the first derivative. The derivative of the derivative. Right? And this is important because it helps us see how the second derivative can be applied. Let's take a look at this function. Okay, this is our function f. Some random function. Now, we're going to slowly travel along the function, but watch what happens to our slope as you start to travel along the function, okay? Now, the first derivative tells you the rate. The first derivative tells you the rate at which f of x changes. Basically the slope, the change in f of x or the change in x, the rate at which f of x changes with respect to x. F prime prime, if you were to extend this analogy, is the rate at which f prime changes. F prime of x changes. And why is this important? Because it helps us expose why the second derivative defines how the graph curves. If you look over here, you see the derivative is pretty high. F prime is much greater. The double greater than sign means much equal. F prime is much greater than 0. Okay? However, as you start approaching over here, it starts to flatten out. It flattens. It flattens out. And it hits this maximum, but it hits this maximum point over here, but that's not what's important in the second derivative. Okay? Because even after it hits this maximum, it still starts to get more and more negative. Okay? So if f prime prime of x is less than 0, that means f prime is getting more negative. More negative. So if it's getting more negative, then you could see it starts to curve downward. And there is a technical name for how the graph curves, whether upward or downward. And that is known as concavity. And that is really important, and that is what the second derivative measures. How the graph curves, whether the graph is concave up or concave down. And if you were to look at this orange part I've highlighted so far, you might notice that this graph is concave downward. It's a frown. It's facing like this. Okay? Which means as you move rightward, the slope starts to decrease. So the slope itself is changing. Okay? So the slope itself is changing. However, just like in the first derivative, there is a magical point for the second derivative as well. And I can probably eyeball it to be somewhere around here. Around here. Okay? And when you cross that point, you see that the graph starts to curve upward. Now the slope is getting less negative and starting to get more positive. Okay, however, it starts to curve downward again for the rest of the graph. So we see that the concavity is changing. Okay, so the orange tells when it's concave downward. So when it's curving downward, and the green shows when it's concave upward. So basically when it's like a smiley face, when it's curving upward. And that happens when f prime prime of x is greater than 0. Because if f prime prime of x is greater than 0, then the rate at which f prime is changing, the rate at which the slope is changing, is increasing. And you could see pretty clear parallels to this. And draw f prime, and f prime prime. Okay? So f prime and f is related by the actual value of f and the slope. Okay? F prime measures how the rate at which f is changing, whether f is increasing or decreasing. Okay? And the max and minimums, the maximum value and the minimum values of f on an interval, or the relative maximum minimum points of f of x. However, f prime prime measures whether f prime is increasing or decreasing. And you can say that's the maximum or minimum slope on an interval before the slope itself starts to increase or decrease. Okay? And this point, or it's a maximum slope, and when the concavity changes. So f prime prime measures concavity. This point is known as a point of inflection. A point of inflection, where the concavity changes, where it changes from curving downward to curving upward. Okay? Or where it changes from curving upward to curving downward. So this is also a point of inflection. Okay? This is also a point of inflection. And if you want to measure points of inflection, you're going to have to use what is known as second derivative. Well, not necessarily. Well, there is the concavity test. Okay? The second derivative test is another test, but the concavity test, which is basically the same thing as the first derivative test, except you apply it to the second derivative. So, step 1. Find f prime prime of x, then set it to 0. Because when f prime prime of x is equal to 0, you can have potential points of inflection. Because that's when the slope itself is at its maximum. So if f prime prime of x and you set it to 0. Then step 2. Check the concavity before and after the, what I could call it, critical points. When I mean critical points, I mean potential points of inflection. Because there are graphs where it misleads you and makes you think that there's a point of inflection where it actually does not. So you have to test to see whether it's actually a point of inflection. Okay? So let me just rewrite this because it's starting to get messy. So if I have a graph of x to the fourth, okay, which sort of gets really flat as it reaches the origin and for a little while, and then it starts to rebound back up. This is f of x equals x to the fourth. Now, what I'm going to do is get the second derivative. So the first derivative is 4x cubed. The second derivative is 12x squared. So if you were to set that equal to 0, then you have x equals 0. Okay? Now we have to check whether it's actually an inflection point. So you do the exact same thing to check whether it's a minimum or a maximum, except you test for the second derivative. Okay? Now, because you have 12x squared, okay, this is positive for all real numbers except at x equals 0. In that case, it's 0. Okay? Which means this part is concave up, and you see it sort of curves up over here. And this is also concave up. Plus, plus. So this is like a dud for the second derivative. This is a dud. Because the concavity is not changing at all. Let's contrast this with x to the third. With x to the third. So we have g of x equals x to the third. So let's find f prime of x is 3x squared. F prime prime of x equals 6x. We set that equal to 0, and you get x equals 0 again. However, if we were to test our number line now, you could see that this is positive when x is greater than 0, and it's negative when x is less than 0. So you could see that it's sort of curving downwards up to this point when it starts to curve upwards again. Okay, so you have downward to upward curves. That means the concavity changes, which means you do have a point of inflection over here. In the next couple of videos, we're going to be doing some actual problems here. And now, one last thing I want to end on, okay, is now we have basically finished experimenting with the first and second derivatives. You usually don't use any derivatives above that. Okay, in AB, usually first and second will do. Okay, so if I were to give you a graph of function f, here's a good one. Okay, this is f. This is f. So let's see if we can draw f prime and f prime prime just with this information. Just draw slightly better axes. Okay, so this is the graph for f prime f prime. Try and make them as accurate as possible. It's f prime and f prime prime. So first you have to do a thorough analysis, okay, of the function f. So you could see that there are maximum points over here. Maximum, maximum, maximum. Sorry, maximum, maximum, minimum, minimum. So you have extrema. Okay? That means at these 3 points, try to match them as close as I can, you have f prime will be equal to 0. Now, you notice that it is concave downward along this entire interval. Until there's an inflection point over here, labeled the inflection point's blue. You have another one over here, and another one about here. Okay, because this is concave up, concave down, concave up. Which means you have some points of, the points of inflection will make f prime prime equal to 0. Now, it's increasing until our first maximum point. And after that first maximum starts decreasing again until it hits our second, which means okay, never mind. So if this is increasing, we could see that f prime will be positive. Okay? But it will be, f prime will be decreasing because the graph is concave down. So f prime will be decreasing. Okay? And then after this maximum, you get this point of inflection. Okay? And if f prime prime is 0, well, f prime was 0 when f had an extrema. So you can extend this, that if f prime prime is 0, f prime is an extrema. So the points of inflection, as a matter of fact, mark the extrema points on f prime, which is kind of cool to think about. Okay, so we have an extrema over here, and it sort of curves up, okay, because it's concave upward, and now we're starting to increase again from here to here. So we're up again, we have another point of inflection. So this is over here, another point of inflection, our second point of inflection. So we have an extrema point over here, and f prime becomes 0 again over here, until we have a maximum over here. Sorry, a minimum. Okay, we have an inflection point, we have an extrema, and it's decreasing. So the extrema point must have a negative value. Okay, so the extrema bounces back up because the slope is again increasing again. Then hits a final minimum point. Okay, so negative to positive. Then it just keeps on increasing. So that's the graph of f. Now f prime prime will be a bit easier. So it's concave down, which means it's negative. Okay? So we're expecting what seems to be a cubic function. So it's concave downward until this first inflection point. So let's draw concave. So f prime prime will be negative. However, here we get our second inflection point will be concave upward. Okay, so f prime will be positive. We should have a maximum somewhere over here because of Rawls' theorem. I hope you still remember that. Okay. So somewhere there's a maximum. These are differentiable functions. Okay, so we have concave upward. Now we should have concave downward again over here. So f prime will be negative. There will be some maximum, I don't know where exactly, but there will be some maximum. Now over here, it becomes concave upward as x approaches infinity. So we're done, basically. And we did it just given the graph of f and using everything that we've learned so far about analyzing functions, we were able to draw with good precision, not the best precision, we don't know the actual values, but with good precision, the graphs of f prime and f prime prime. Thank you. See you in our next video.